Welcome back. Welcome to our new lecture in power system. I hope you and your beloved one are safe in this pandemic, and I hope the coronavirus impact will end soon. Today's lecture, it's about lossless transmission line system. The transmission line system, as we studied in the past few weeks, it's a very important element when it comes to our power system network. During today's lecture, we are going to capture multiple concepts under lossless line. So we are going to capture the following concepts. Number one is surge impedance. So we are going to cover the surge impedance. Number two, we are going to capture the ABCD parameters for a lossless line. So far, we've done ABCD for short line, medium line, long line. Now, we will create one, or we establish the ABCD for lossless line. A, B, C, D parameters. So after we do the ABCD parameters, after we do the ABCD parameters, we are going to study the equivalent pi circuit representation, the equivalent pi circuit. And after we do the equivalent pi circuit to just represent any type of transmission line into pi, and then we focus on the lossless line. After we do this pi, we will do the wavelength. The wavelength of our transmission lines. And after we do the wavelength, we will do stuff called surge impedance loading. Surge impedance loading. This concept will give us the maximum power transfer under lossless line. We will go through each one of them. And then after we do the surge impedance loading, we will do the voltage profile for the transmission line. We do some stuff called voltage profile. And then finally, we will talk about the steady state stability limit. Steady state stability limit. Now, so during this week, we are going to cover all this. Based on the information that we captured in the past few weeks, this will be easy to comprehend, will be easy to determine. You will see now. You will see. Now, this concept will lead us to a very, very important statement. This concept will lead us to a very important statement. These days, whenever we design a transmission line, we design a transmission line that have very low losses. No one accepts the design of a transmission line that has high P losses, real power losses. So this concept that we are going to learn today, they're going to be simplified because of the lossless condition of the line. which means it is acceptable for me to use it as a hand calculation to do a quick assessment of my transmission line at the initial stage of the design, and then initial stage of the project or the assessment or the pre-design. And then I can use a complex or advanced software, computer software program tool to complete the detailed analysis, the detailed design of my transmission line system. So that's why we are going to capture, we're going to spend a lot of time in this concept. This concept, it will aid the engineer to use hand calculations to assess the pre-concept of the transmission line and see its characteristic, its limitation, especially from a voltage profile, transfer power, capability of power, steady state, stability, limit, all this information which are very, very important to our system. Now, let's start. So now, let's start. Let's start with the first one. Now, the first one, surge impedance. Let's recall two elements from the previous one. We have Z, if you remember ZC, of. Do you remember this? Square root of Z over Y. Remember this? Now, under the lossless line, because I have a lossless line, that means I have R, it's equal to G, it's equal to 0. That means I have R, it's equal to G, it's equal to 0. I have no real losses in my transmission line. So Z, in this case, Z will be J omega L. Y, it's equal to, what will be Y equal to? Only the capacitance, there's no G. So J omega C. So if I put it together, it will give me ZC L over C. So this characteristic impedance, it's now known as surge impedance, which is the surge impedance, which is known as the surge impedance. Is that clear what a surge impedance? Surge impedance is the characteristic impedance of the normal transmission line under lossless. It's equal to square root of L, the inductive, divided by the capacitive component, which is known as a surge impedance. Let us now recall the propagation constant. If you guys recall the propagation constant, remember it's a square root of, if you remember, square root of Zy. If I do the same this it's equal to, for a lossless line, J omega L. So I have, on the outside, I have J omega L C. J omega L C, which is equal, in this book, they call this as beta, which is equal to J beta, where beta is omega square root of LC. Is that clear? So now I've done nothing basically. All I've done is the characteristic impedance of a normal transmission line under lossless line will be equal to square root of L over C, which is the surge impedance. Let me rephrase surge impedance into normal English. Surge impedance occurs when I have the capacitive and the inductive powers matching. You will see when we do a lot of the surge impedance loading, you will see what I'm trying to say. Let's now do it step by step. There's no need to rush into any system. Now, what I want you to notice is this system and this system. Now, the surge impedance, it's a purely 100% real value. While this now became J beta. So it's 100%, it's a totally imaginary. So the propagation constant now, the propagation constant now, it's purely imaginary. This is only real value. See, so this is 100% imaginary value. See, this is 100% imaginary value. So is that clear so far? Okay, let's now move to the next item, which is the A, B, C, D. Let's move now. Take a moment to capture all this information. Get a different pen. And take a moment to capture all this information, and then we will start the ABCD. Now, this is number 2, which is the A, B, C, D parameters. Let's recall the numbers that we did in a long transmission line. A, it's equal to cosine hyperbolic of, guys, we did use L, if you remember L. Now, because we have L as an inductor, so we don't get confused between the length L and the inductor L, because as you can see now, ZC, the surge impedance ZC of L over C, and the propagation it's equal to J beta this L is for the inductive component. That's why I wanna say now that length is used X, so I don't get confused. Okay, between the length L and the inductive, as we did in the last lecture. Okay, so what's this cosine hyperbolic when it comes to lossless line? Guys, what's the definition of a cosine hyperbolic, if you guys remember? Cosine hyperbolic of x, it's equal to exponential of this x plus exponential of minus x over 2. Look, guys, hold on a second. Well, what's this one now? Look, this is a purely imaginary. See, it's a purely imaginary. So therefore, for me, cosine, it's equal to J beta x plus hold on, this is a complex number. Exponential of J alpha, J A, that's a complex number. So if I spread it down into the cosine A plus J sine B, if I do it, I will end up with this equal to, this will be equal to cosine beta x. So can you see now, this is now my A and D now, for a lossless line, it's a cosine beta x. Can you see the simplification? Previously, I had to use cosine hyperbolic. Every time I am going to do some hand calculations, I have to put cosine hyperbolic for this value. It's exponential. Now all I do is cosine beta x. And remember, A and D are per unit. There's no unit. Remember this? Okay, great. I do the same for, remember what was B equal to? And then I do C. Do you remember what was B equal to? B is equal to ZC. Do you remember ZC sine hyperbolic? Remember I put an X in here. If I keep going through this, if I do the same calculation, I will end up it's equal to the sine hyperbolic. This is equal to ZC. Sine hyperbolic is exponential of minus again this imaginary, which is equal to ZC exponential of J beta x minus exponential of minus J beta x over 2. If I analyze this circuit, I will end up with ZCJ. I will end up with this answer for B. It's equal to ZCJ sine beta x. We've already determined what ZC in respect of vectors. It's equal to J and this unit is this unit is ohm. Is that clear? Let's take a moment to comprehend this before we delete this section. So all I'm doing is ZC, the propagation, I convert it into the lossless element, and then I rechange A, B, C, D to captures. So now, if I do the same for C, let me write down. If I do the same for C, do you guys remember what was C? C it's equal sine hyperbolic divided by ZC. If you remember, C it's equal to sine hyperbolic of divided by ZC. Sine hyperbolic, it's going to be minus, if you remember, it's going to be J sine. So this answer will be equal for a lossless line. C will be equal to sine divided by ZC, and we don't want to forget the J. And this is in Siemens unit. And we know what's a ZC is square root of L over C. Square root of L over C. Can you see all this justifications, all this reduction in complexity for a lossless line? And like I said before, nowadays it's unacceptable to design a line with a high P losses, real power losses. That's why I can use these simplifications that I did from hyperbolic to normal sine or a cosine. to determine, to have a quick calculation about my transmission line performance, and then after I decide this is acceptable for me, when I want to go into the detailed design, detailed analysis of the transmission line, I use a computer-aided software to do this system. Is that clear, guys? Okay. Now, this is the ABCD. So as you can see, the ABCD basically transferred from hyperbolic into normal, sine and cosine. Please write down the new ABCD for a lossless line. Now, the next one. What was the next one? Number 3. We said we are going to do the pi circuit. I want to be able, this is a pi circuit. I want to be able to represent any transmission line using this transmission line. VR, it's equal to magnitude of VR angle 0. This is IR. This is Y dash over 2. This is Z dash. This is Y dash over 2. And this is Vs. It's equal to magnitude of Vs angle of delta. And this is Is. The pi applied to any transmission line. Short transmission line, this is 0. Medium transmission line, this is equal to Y over 2, if you remember. For a long transmission line, that's what we are going to find out. What will be Z dash, Y dash over 2, Y dash over 2 for a long transmission line, which is also, all we have to do is convert the cosine hyperbolic or the sine into the lossless line. Okay. For a long transmission line, what do I have? A? It's equal to cosine hyperbolic, if you remember, of x. Remember, I'm using x now because I don't want to confuse between the length and the inductive component. Okay, perfect. Great. This is for a long transmission line. A, it's equal to, D as well, it's equal to cosine. Remember, when I did the transformation into lossless line, A, it's equal to cosine beta x for a lossless line. I want to obtain now Y dash and Z dash give values in respect of a long transmission line and a lossless transmission line. I want to do these two elements. Let's start for the first one at the moment. Let's start with this one at the moment. Great. Hold on a second. If you remember the short transmission line and the medium transmission line, this is equivalent to a medium transmission line system. Do you remember this? If I recall A, B, C, D, if I recall A, B, C, D for a short line. If I recall A, B, C, D for a short line. A, it's equal D. This is a short one, isn't it? A, it's equal D. It's equal to 1 plus Z dash Y dash over 2. If I do the analysis as per the short transmission line, perfect. Then B, it's equal to Z dash, and I C, it's equal to Y dash, 1 plus please guys, please go back to the video titled Medium Transmission Line Analysis. These values are obtained based on our previous lecture for a medium transmission line performance. Perfect. Hold on a second. What's B? It's equal to ZC sine hyperbolic which is equal to, perfect for me. So now I know that this value, it's equal to this. So now I'm doing the pi circuit representation of my transmission line. I know that Z dash is equal to this. And I know also what's B for a lossless transmission line. Can you see the link now? I already have B for a lossless transmission line. So therefore, Z dash for a long transmission line is equal to ZC sine hyperbolic of lambda over time x. And for a normal transmission line, it's equal to J. Remember the complex. J ZC sine beta x. Okay? Sine. Remember. Okay, perfect. Great. Now, all I want to do now is determine what's y dash over 2. That's what I need now to determine y dash over 2. Look guys, I look at this one, A, it's equal to cosine hyperbolic x, which is equal to 1 plus z dash y dash over 2. Z dash already found to be ZC, already found to be, remember ZC sine hyperbolic. So now I can say that y dash over 2 it's equal to cosine hyperbolic minus 1 divided by z dash. Divide by z dash. Is that clear? Look now, I found this value and I found this value. Irrespective of long, if you want it to be in medium or a short or a lossless transmission line, all I have to do is represent A, B, C, D with its values. Is that clear? How do I establish that pi? How do I establish the pi circuit representations of a transmission line? All I have to do is find ZC and Z dash and Y dash over 2. Now, in your book, in the book that we study in, they went into an extra step. They went into the extra step where they found the function, of the conversion between Z dash and Z. So what they said in the book, they said, hold on a second, I need to establish a function. Which is said I want to have Z dash, it's equal to Z function 1. And then I want to have Y dash over 2, it's equal to Y over 2 function 2. Function 2. Now, if you go ahead and you do the calculations, which is we are going to do it. If you go ahead and do the calculations, let's start with Z dash. Z dash. Remember, before we go ahead, before we go ahead, I want to clarify two elements. This Z dash, or the big Z, it's equal to this Z, it's equal to Z, small z, multiplied by the length. If you remember from the short transmission line, Z multiplied by length. This Z, the unit is ohm per kilometers. Is that clear? Is that clear, this relationship? Do you remember this relationship? So now, let me go back. It's equal to this. What did we find? What did we find Z dash equal to? What did we find Z dash equal to? If you remember, we found it equal to ZC sine hyperbolic of, this is what we found Z dash equal to. Perfect. What's ZC? ZC. What's a ZC? If you remember, square root of Z over square root of Z over L. Sorry, Z over Y. Small z over small y. So all I have to do is, I need to find, hold on a second, I need to find this z. So I need this equal to, I need this in this format, z times f1. What's z? What's z? It's equal to, so this, I can say that z dash will be equal to z times the length L, z times the length L, let's keep it x as we put x, zx multiplied by zc sine hyperbolic x, and then I will divide by zx. So basically I've done nothing. All I've done is multiply by zx, divide by zx. Haven't done much. Okay, great. This give me this system, it's big Z. It's big Z. Multiply by, what's ZC? ZC is square root of Z over Y sine hyperbolic of x divided by zx. See guys, if you take this relationship, this will give us z multiplied by sine hyperbolic lambda x over lambda x. What's this lambda? Remember, it's the root of zy. Remember guys, this lambda, put it here so it can be clear. This lambda is square root of this square root of zy times the distance. That's why if I take this z, this is z squared, if I take it inside the system, I take this, end up with yz square root of yz x, which gives me this system. So this is now f1. This is the function f1. Guys, in the exam, you will be allowed to bring your equations. So don't worry about this, to memorize this equation. However, I can ask in the exam, show me the analysis that leads to the function f1. Similar I can do for the function f2, which is I will post all these solutions for you online. Actually, it's in your book section. It's in your book section 5.4. It's in your book section 5.4. Yes, that's correct. Section 5.4. Now, so this is the pi representations. The pi representations, the pi circuit representation of a transmission line allows me to use any transmission line into the pi format using the value of z dash and y dash over 2. And I go back, normal analysis. When I come to lossless line, when I find z dash, all I do is the cosine hyperbolic and the sine hyperbolic, and all this will goes back to cosine or j sine beta x. Is that clear? Is that clear? Now, number 4. We are going to do surge impedance loading. Surge impedance loading. What's a surge impedance loading? I think so. That's number 4 that we said we are going to do. Now, the surge impedance loading. Before we do this, let's do the power S. Let's do the power S. Guys, let's talk about one phase. I'm talking about if it's a 3-phase system. Let's do it for one phase. Take one phase out and do SX. It's equal to. What's SX equal to? It's equal to VX. Remember this? What's Vx equal to? What's Vx equal to? And what's Ix equal to? Come on, guys. What will be Vx? Guys, look, remember I'm talking about transmission line. What's Vx and what's Ix? Remember, I have AVR plus VIR. Remember, if I go back and I recall, V of X, it's equal to, remember, V at point X, it's equal to A, VR, plus B, IR. And Ix, it's equal to C, VR, plus D, IR. For a lossless transmission line, I know A, B, C, D values. I know A, B, C, D values. Correct? Is that clear? What's a surge impedance loading? The surge impedance loading happens when I have a resistive load connected at the VR, across the VR, has the same magnitude as a surge impedance. So I have this, I have a transmission line, I have now I have the same magnitude L over C. This is a known. This is IR, that's a VR, that's a VS, that's IS. That's IS. So let's analyze the circuit. Let's analyze the circuit. Guys, this is cosine beta x. This is cosine beta x. This is J ZC sine beta x. Sine beta x. Okay. What's IR equal to? What's IR? IR is a VR divided by Z. From the circuit, from the below circuit, from this circuit, I have IR, it's equal to voltage VR, it's equal to VR over ZC. So let's put it, I have Vx, it's equal to cosine beta x VR plus J ZC sine beta x IR multiplied by VR over ZC. This and this can go. Is that clear, guys? This and this can go. So look, based on this information, what do I have? VR, I'll take on the outside. So Vx, so therefore, Vx is equal to VR cosine beta x plus J sine beta x for a lossless transmission line. Guys, this value, it's a complex number, E of J beta x. It's only represent an angle. So therefore, based on this system, based on this, I have the magnitude of Vx, it's equal to the magnitude of VR. Can you see based on this? Is that clear, guys? This is very important, guys. The surge impedance loading, it's a very, very important element for me. So now, I have Vx and VR have the same magnitude, as of, it's equal to Vx is equal to VR exponential of J beta x. If I do the same for I, for the current, if I end up doing the same for the current, I end up with Ix. If I do the same for the current, I end up for Ix. It's equal to exponential of J Vx divided by Zc. VR, because we're interested in VR, divided by Zc. So I have this equation and I have this equation. If I go back and put the S, if I go back, guys, remember I'm interested into the power S. If I go back and put S, X, if I go back and I put S, X, it's equal to Vx, Ix conjugate. Vx it's equal to exponential Vr exponential of J beta x multiplied by, look, exponential of J beta x Vr over Zc, this is conjugate. Guys, the conjugate Zc, it's a pure resistive. So the conjugate is exactly the same. So what do I have? I have Vr, this it's equal to Vr magnitude squared over Zc. This will be equal to magnitude Vr squared over Zc. Can you see? Because guys, if you remember this multiplied by the conjugate of the same value, which is give you the magnitude squared divided by Zc, divided by Zc. Now, it's clearly shown the real power transfer along lossless at surge impedance loading remain constant. So as you can see, any distance of x, the power everywhere it's the same. Because remember, I did it in x, irrespective of what's L, the length, irrespective of what's the length. Can you see now that the power along the transmission line remain constant of these values? Remain constant of these values. from the sending end to the receiving end. I did not change from the sending end to the receiving end. I have always the power constant. And the reactive power, as you can see, is zero. The reactive power is zero. Because, like I said to you earlier, the surge impedance loading happens when the capacitive induction and inductive, balance each other. Is that clear, guys? Is that clear? Or it's not clear? Okay, guys, this is the importance of the surge impedance loading. The surge impedance loading for a lossless line shows that the power along the transmission line never changed from the sending to the receiving end, and the reactive power is zero. Is that clear? Okay. We missed doing the wavelength. The wavelength of a transmission line, the wavelength of a transmission line is 2 pi over beta. Part of your course, part of this power system 1, we are not going to go through the calculation of it. When you go to power system 2, in your book, chapter 13, which is under power system 2, we will capture this requirement. However, beta, remember, beta, it's equal to omega. Remember this? Beta, it's equal to the omega square root of LC. So therefore, I have now lambda times the frequency, it's equal to 1 over square root of LC. That's what I want you to know based on this course. There is no need to calculate where did this come from under the content of our course. Is that clear? I hope that's clear. Now, we spoke about surge impedance loading. I want to show you now a sketch, the voltage profile of a transmission line. I want to show you now the voltage profile. I want to show you now the voltage profile. What's a voltage profile? This is the sending voltage, Vs. This is under Vr, under surge impedance loading. This is Vs will be equal to Vr. See, this is a voltage level. Vs, it's equal to Vr. This will be under no load. Why under no load, guys? Why it's high under no load, the V receiving? Because, guys, look, Vr, if you remember, it's equal to Vs divided by A, which is cosine beta x. Vs divided by cosine. Cosine almost maximum can be 1. This will be under full load. This is the system, and this all the way to 0 under short circuit. If a short circuit happens at the load, Vr is 0. Is that clear? Is that clear, guys? Look, this is surge impedance loading. I have Vr is equal to Vs, straight line, doesn't change the voltage. Under no load, I have Vr. This is on the assumption that I'm looking at it when it's fixed, goes up. Full load, this is the sketch for it, the voltage profile, and this is the short circuit profile of a voltage. This is the short circuit. Utility, engineers inside the utility use this graph to determine the full load, short circuit, surge impedance loading. So the perfect for us if we can achieve these values, because I have no losses. But in reality, It's almost impossible to achieve this value, and this is no load. That's known as the voltage profile of a transmission line system. That's known as the voltage profile of a transmission line system. The last stage is, the last element I have is the steady state stability. What's a steady state stability? Let's look at it now. So if I have the circuit, remember, I go back and I sketch my circuit. I use a pi module. This is VR, it's equal to magnitude, voltage, angle 0. This is IR, that's VS, equal to magnitude of VS, angle of delta. This is y dash over 2, z dash, y dash over 2, y dash over 2. Guys, pay attention what I'm going to do is, at this node, what do I have? I have, at this node here, at this node, I have Vs minus Vr over Z dash. It's equal to IR plus Y dash over 2 Vr. Is that clear? So therefore, IR is equal to Vs minus Vr over Z dash minus Y, this is Y dash over 2 Vr. Guys, all I want to go back now, the reason why I want to determine S receiving, which is equal to Vr IR dash. Remember, I'm talking about one phase now. If it's three phase, I use root 3 V line I line. And if it's single phase, I use this one. If it's a three phase, I can use 3 VR IR. Conjugate, remember the conjugate. Okay, great. Guys, look. I have now VR and I have IR in respect to VR. So therefore, it's equal to, what's S equal to? I multiply it. I multiply this, which is equal to, guys, pay attention, it's equal to VR multiplied by Vs minus Vr over Z dash minus Is that clear? Is that clear, guys? What's Vs? If you remember, what's Vs in respect to Vr? What's Vs in respect of Vr? I can find the relationship, however, I keep going. Can you guys do the quick calculations and tell me what would be the power receiving at the end of this one? All I have to do now, guys, remember this, remember Vs, remember guys, remember these elements. Vs, it's equal to Vs exponential of J delta. Remember, has an angle of delta. Vr, it's equal to Vr because the angle is 0. That's I always take the reference is a load, angle 0, and I work backwards. So now put this one. This will be represented by Vs exponential of J delta. This will be represented by Vr. We know what's Z dash, isn't it? We know that this Z dash, if you look at it, it's a Jx dash. Remember, under lossless line, it's only purely inductive. Remember, purely inductive. There is no R inside this. And I put it down. At the end, I'll end up with SR, it's equal to Vs, Vr, divide by x dash sine delta. This is the receiving power. This is the receiving power. When it is maximum, P max, it's equal to Vs Vr over x dash. This system will reach the maximum when sine delta is 1. That means when delta is 90 degrees. Delta is 90 degrees. Also, this system equal to, if I convert everything to per unit, system, it's equal to Vs per unit, it's equal to Vs per unit multiplied by Vr per unit divided by, I have to use now, that's why I did the wavelength, sine 2 pi L over lambda, sine 2 pi x over lambda, the SIL. The surge impedance multiplied by the surge impedance loading. Multiplied by the surge impedance loading. And the surge impedance loading is equal to, you remember what we did this? The surge impedance loading, it's equal to VR squared divided by ZC. From the previous one. The maximum power, when we did this, it's equal to, remember the power under the surge impedance loading? Now, this Pmax, see this Pmax in here? Represent the maximum possible power that the transmission line can transfer theoretically. And if the power exceeds this value, you will lose the synchronization between the sending and the receiving voltage. Is that clear? That's the importance of a transmission line system. Guys, I know today we went through a lot of materials. This materials is going to be studied during the entire week. And we are going to do an example on each element. What I want you to take, the following element from it, the following element. Element number one is, what's a lossless line? Lossless line is when R and G equals 0. Therefore, I can simplify my parameters as we saw, the A, B, C, D parameters. I can also represent using pi circuit representations by using finding Z dash, Y dash over 2. Also for a lossless transmission line, all this will be in a form of cosine, sine, and tangent. And then what I've done, I found the surge impedance loading. Under surge impedance loading exists when I have ZC, when I have a load, purely resistive load, connected across the V receiving, has the same magnitude as the surge impedance. And then I saw that surge impedance loading is V squared over V receiving squared over ZC. V receiving squared is the rated voltage basically of the system, because I always take it as a reference. That's my interest. I always take it as a reference. And then after I did this, I found the voltage profile. So if I have the voltage above, when I'm reading, I have the voltage above the voltage sending, I look at it, hey, it's at no load or a very light load. If I have the load is very heavily away from the surge impedance loading voltage, I look at it that it's a heavily loaded system. And finally, I did the steady state stability. I determined the Pmax that transmission line can withstand, which is in relation to the wavelength, the length, the surge impedance loading, and this system in here. If I try to exceed the system theoretically, I will lose the synchronization between the sending and the receiving end. I know that's a lot of information to cover into one lecture. However, we're going to split it into the entire week. So now we we'll study this element, and then we will go to a lot of practice examples. So let's now take a few minutes rest, and then we will continue doing the actual examples.